In this video, we're going to be introduced to mass spectrometry. Notice I did not say mass spectroscopy, which is looking at the change in a molecule based on the absorption of electromagnetic radiation. So mass spectroscopy is used extensively in our society, even though you may not have known it. For example, it's used in airports nowadays to check for explosives. Recently, they have introduced sampling your skin on your finger. And what they're doing is they're using a mass spectrometer to detect whether or not you have residue that could be explosive on your fingertips. It's also been used for decades in automobile emissions to determine the concentration of carbon dioxide that's coming out of your exhaust. And of course, we all know about artificial steroid use in sports. And so this is how they essentially detect whether or not an athlete is using artificial steroids. Now the general scheme of a mass spectrometer kind of looks like this. And if you've had general chemistry, I know that when I teach general chemistry, I showed this scheme to my students very briefly. And of course, here, I want you to simply understand what's going on. I will never ask you to, draw out a diagram of a mass spectrometer. But in essence, what is happening is on the left-hand side, you see sample M, and M stands for any molecule, and that molecule is placed into the spectrometer where it is bombarded with high voltage electrons. It then passes through a narrow slit that is negatively charged because what happens is once the molecule is bombarded with electrons, it takes on a positive charge. So now it passes through a negatively charged slit so that it begins to accelerate. And as it accelerates, it then passes through a magnet. Now, based on its mass and its charge, there's going to be a slight variation in the change in direction that is caused by that magnetic field. So the lower molecular weight ions are deflected a lot, and the high molecular weight ions aren't deflected as much. And so we can basically then analyze through a detector and separate ions based on their mass to charge ratio. Not necessarily their mass, but their mass to charge ratio, because ions, if a molecule ionizes into a +2 charge, then it's going to have a greater effect on the magnet. So that's something to think about, but later on down the road. And we'll really never explore mass spectrometry in that great of a detail, looking at molecules that have ionized to a +2 or a +3 or +4 state. We're basically going to be looking at molecules that have ionized once to a +1 charge, and therefore the mass to charge ratio really is the same as the molecular mass. So just a brief idea about what is happening in that mass spectrometer is that when you bombard a molecule with high voltage electrons, you create what's called a radical cation. So the idea is I take my molecule, I bombard it with high voltage electrons, and they essentially kick off an electron because of electron-electron repulsions. The result is that now I have a radical, right, because one of the electrons has been discharged, and the molecule has now a charge of a +1. So it is a cation, a radical cation. And we refer to this radical cation as the molecular ion. Now, one of the results of the conditions of our initial formation of that molecular ion is that because of the high energy electron source, that radical cation can fragment into smaller pieces. Here's an example of a typical mass spectrum. and this is of toluene, as you see on the left. Now, toluene, you can see the molecular ion peak farthest to the right of 90 um, 91, no, excuse me, 92 units, right? So that is the mass of toluene itself. And then you see all different types of fragments that are smaller than the molecular ion peak. And that's because what's happening is you get fragmentation. So for example, a proton can easily come off, and you end up with a mass that is 1 unit smaller than the molecular ion peak. But also other things can fragment off, and so you get these little tiny pieces. One thing to note is that the molecular ion peak, it's actually not the thing with the largest mass. If you take a look to the right of the molecular ion peak, you actually see a very small peak that that is 1 unit greater than the molecular ion. And this is what we refer to as the M+1 ion. And that essentially has to do with the different types of isotopes of both hydrogen and carbon in toluene. Remember, hydrogen can have an isotope H2, so deuterium. Carbon is typically carbon-12, but it also has an isotope of carbon-13. And so those little contributions of different isotopes add up to what's called an M+1 peak. That's important if you get into great detail about mass spectrometry, but for our purposes, we won't worry about it too much unless we're looking at specific isotopes of, for example, halogens. And we'll explore that later on through the semester. So the key is remembering that you can only visualize, so a mass spectrum only visualizes charged species, namely positively charged species. And as an example of this, I want to show you the mass spectrum of neopentane. So neopentane, when it fragments, you get a molecular ion peak. Now, if you calculate the mass of the molecular ion peak, you should see a peak at 72. And notice we don't see that peak at 72. The reason for this is because as soon as the molecular ion is formed, it actually is fairly unstable, and it readily dissociates into a tert-butyl carbocation, which is shown at the bottom reaction. So notice there's actually two things that could happen. You could get, you're getting a carbon-carbon cleavage, and one result is that you form a tert-butyl radical and then a methyl carbocation. And that methyl carbocation has a mass to charge of ratio of 15, which if you look at the spectrum, you do see a small peak at 15. So that happens a little bit. But you can also get a tert-butyl carbocation and a methyl radical. And the tert-butyl carbocation has a mass to charge ratio of 57. And this is the prominent peak in that structure. So one of the things with mass spectrometry is we do have to be careful about recognizing where the molecular ion peak is. Every once in a great while, we won't be able to see it, right? But for the most part, and for beginning or beginners looking at mass spectrometry, the molecular ion peak either will be shown or it will be given to you.